So, we will continue with what is called turbulence stresses or Reynolds stresses. Okay, so this is the extra terms which are going to be coming in because of the fluctuation terms. Okay, so to illustrate this, let us consider a two-dimensional boundary layer equation. Here you can see that the derivative in the x direction is not prominent as the derivative in the y direction. So, the diffusion term basically does not have the x derivative, and since the turbulence is time dependent, so we have included a time dependent term also here. So, dou by dou t of rho u, the x momentum equation, equal to dou by dou x, the convective term, dou by dou x of rho u and dou by dou y of rho u v, and this is written in conservative form. So, writing like this is conservative form, and you can see this the diffusion term in the right hand side. So, this is what we are taking into account now, and let us do the Reynolds decomposition, where you know that the u is at any time instant t is written as the time average value plus the fluctuating value, again which is a function of time. Similarly, u v also you do the same. V dash. So, once you do this, the assumption, one more assumption which is made is the rho and mu, the properties are assumed to be constants here. So, if it is not, then we have to that will also fluctuate, and that also should be added like a mean and the fluctuating quantity. So, just to illustrate the stress terms, let us consider rho and mu to be constants, and Reynolds decomposition we will do like this, writing a flow variable, flow velocity as the mean value plus the fluctuating value, that is the decomposition, Reynolds decomposition. And time average, you know how to take this. Time average is nothing but you have to take considering a longer, sufficiently long time period, and average the fluctuations. Okay. So, once you substitute this in the equation, okay. So, for example, for u you substitute u bar plus u dash. So, here you have to write u bar plus u dash. Similarly, for v you can write here v bar plus v dash. Okay. Then what you do, you have to take time average of the entire equation. Now, if you take time average and since we are assuming this, that is the x derivative is much less than the y derivative, the x derivative term of the fluctuations. So, you get derivatives like dou by dou x of u dash, dou by dou x of v dash, etc. Those things we will neglect. Okay. So, neglecting the x derivative of the fluctuations, we will get this equation. Okay. So, you can see that this equation, if you take the time derivative, we have the mean value of the time derivative. So, you can say u dash bar will be equal to 0. So, you can see that dou by dou t of rho into u bar will come. Similarly, the convective derivatives basically remain the same with the overhead bar, indicating that they are mean values. However, the extra term which has come here is this dou by dou y of, because I have already neglected the x derivative of the fluctuations, but keeping y derivative fluctuations, you see dou by dou y of rho into u dash v dash is there in this. So, that actually comes in from the convective term. So, this term comes in from the convective term, but it is convenient actually to write it in as a diffusion term. So, we have put this in the right hand side along with the stress term. So, along with the stress term we have put this in, and this particular term is now called Reynolds stress. So, similarly, if you do it for x momentum, y momentum, everything, you will get additional terms. These additional terms will create closure problems. So, for example, continuity equation can be written as so, continuity equation is written as this. So, when in general if it is laminar, this term will not be there, the last term will not be there. So, we can solve continuous equation and experimental equation to solve the variable u and v. So, but the thing is now the additional terms have come. So, number of unknowns are higher than number of equations. So, this is called closure problem. Okay. So, that is what we get. So, one more thing what we should understand here is when you do this for continuity equation, you get the average, the continuity is obeyed by the mean value as well as the fluctuation value. So, even the fluctuation value, the fluctuations of V2 that will obey the continuity. So, continuity equation this is actually used for understanding the relationship between u and v, basically this u and v. So, you have to understand that u dash v dash bar is not equal to 0. Okay. Similarly, we have already seen that u dash square bar is not equal to 0. So, u dash bar is equal to 0, v dash bar is equal to 0, etc. So, individually they are 0, but when you say u dash v dash and take average, the product of that will not be equal to 0. So, that is the contribution by this term here, and that is going to be the extra term which is called Reynolds stress. Please understand that this term comes actually by the convective equation, convection terms, but it is now clubbed with the stress term and it is called Reynolds stress. And since the additional terms appear, you get into what is called the closure problem. So, somehow you have to go about solving this. So, when you do not do the Reynolds decomposition, we have to go to direct numerical modeling, as I told earlier. We have to go to extremely smaller grids, extremely smaller time steps, and the bigger problems cannot be done. Very small problems can be attempted with DNS. Okay, now eddy viscosity. The simplest concept what we have is to just take out the closure problem. What we try to do here is the Reynolds stress term is modeled. That means some change we make to the Reynolds stress term. For example, if you go back, the term the right hand side I can write like this. See dou So, these two terms I am writing here. So, dou by dou y of mu into dou u bar by dou y minus dou by dou y of rho into u dash v dash bar. So, this now I can write as dou by dou y of mu into dou u by dou y of u bar plus minus rho u dash v dash bar. So, that this term is what now is written here. You can see this. So, now dou by dou y of minus rho u dash v dash bar is now written as plus rho e into dou u bar by dou y. So, what we are trying to see here is see this mean term, we have viscous stress here, this is the shear stress here. So, the viscous stress, this is the molecular viscosity, dynamic viscosity, molecular dynamic viscosity that contributes to the this first term here, molecular dynamic viscosity. The second term is due to the turbulent fluctuation. So, we introduce a viscosity called eddy viscosity, which is nothing but rho into this epsilon. So, this basically, so if you write this dou u bar by dou y, I say this is equal to minus rho into u dash v dash bar. Okay. So, basically minus u dash v dash is a positive term. So, u dash v dash when you multiply that is actually a negative term. So, that can be illustrated by the continuity equation here. So, as I told you, the continuity is obeyed by the fluctuation terms also. So, now if you write this, you can understand that dou u dash by dou x can be written as minus of dou v dash by dou y. So, if let us say if in the x direction the fluctuation increases, u dash increases, then that means that in the negative y direction V dash will increase. So, this term u dash V dash will be negative. So, negative of negative will be positive. So, this is the term what you substitute for this and put it here. So, this is called eddy viscosity. So, basically, so that is what we are or we can say turbulent viscosity, eddy viscosity or turbulent viscosity, which is nothing but rho e. So, now the effective viscosity mu effective, which is contributed by the molecular viscosity plus the eddy viscosity. So, this is the why we concentrate on this, because see we can see that the diffusivity is one which is much enhanced. Okay, even though you have to keep in mind always that this term is generated by the convective term, but the effect of turbulence is basically to increase the diffusion. Molecular diffusion is slow, but this basically increases the diffusion mixing. So, you can see that when you add this the mu increases. So, mu by rho basically. So, mu increases, then you can see that the diffusion term will be stronger, and this is what is contributed by the turbulence. So, these fluctuations basically increases the mixing. So, the diffusion strength, and so when you have effective viscosity, that will be equal to the molecular viscosity plus the eddy viscosity or the turbulent viscosity. So, this is turbulent viscosity or eddy viscosity are the same. So, now this is the simplest model where you can say that the effective viscosity will be say several hundred times more than the normal molecular viscosity. So, that is the effect of say when the intensity increases, the mixing will be increased. So, that is what the contribution of turbulence is. Okay. So, this is a simple model. So, it is called just we concentrate on this. So, zero equation model, we do not need any additional equation for this. There are several other models, Prandtl's mixing length based models and so on. In fact, to evaluate this we need the Prandtl's mixing length. Okay. Next is to improve this we go for what is called two equation models. I am not going to go to details, but I am just mentioning this. In the two equation model we have an equation to be solved for turbulent kinetic energy. So, that is the first equation we solve, and a second equation is for solving what is called eddy equation. So, we have what is called k epsilon equation, k omega equation and so on, where you solve for the k is the turbulent kinetic energy and epsilon omega are some form of eddy dissipation. So, when you solve this, then the stress terms are modeled using this basically. So, we have to handle the closure problem. So, for which we handle this. So, for example, if I write this in the simplest way, minus rho u dash v dash bar is written as rho epsilon times dou u bar by dou y, then you can see that I call for some effective viscosity here and try to solve this. Okay. So, that is the call here. Similarly, higher order model, this is two equation, then Reynolds stress model that will solve for all the terms appearing like this. In a 3D we will have 5 or 6 terms. So, for all this we will model this, we will have a equation, separate equation to solve. So, that is solved by the Reynolds stress model. So, 5 equation model. Okay. Then we go to what is called large eddy simulation, which resolves for larger eddies, but you do not go for the resolving smaller eddies, that is modeled. So, it will model the smaller eddies and resolves the larger eddies. In the k epsilon k omega models, you model whatever be the size of the eddies, just model it. Here in the large simulation, the large eddies are modeled. So, you go for final grids to model the larger, to resolve the larger eddies. However, the smaller ones are modeled. Okay. So, this is, if you take any turbulence book, you will understand more about the turbulence modeling, and it is not so easy to understand all this. So, for our basic course, we need to understand that the effect of turbulence is going to affect the flame structure both in premixed as well as the turbulent regime for non-premixed flames, turbulent regime premixed and turbulent regime non-premixed flames. So, we need to understand how we are going to understand the effect of this mixing and the eddies interaction with the reaction zones and so on. So, that is what our thing is. Now, you have to understand the extra terms which are going to come and how we are going to model it. Okay. Now, let us do a simple analysis of an axisymmetric turbulent jet. We have already seen the axisymmetric laminar jet analysis. So, now let us try to see how we can apply this eddy viscosity what we have introduced here to solve for the turbulent jet. So, axial momentum conservation equation is written here. So, Vx, please understand that we have to put bars here, but I have removed the overhead bars for simplicity. So, all are mean terms, mean values. Okay. So, you can see that the axial momentum conservation Vx into dou Vx by dou x plus the radial velocity Vr into dou Vx by dou r equal to 1 by r dou by dou r into epsilon times dou Vx by dou r. So, this is the radial diffusion in the radial direction. Okay. So, this is the equation we have, and of course, the mass conservation. Again, please see that are all mean quantities, mean values only. Okay. So, here since we are writing like this, you can see the similarity between this equation and the previous equation. So, the laminar jet solution is applicable here. One more thing is, please understand that we have seen that mu effective will be equal to mu plus here rho e, rho epsilon, correct. So, here this is very small, so we have neglected this also. So, the dynamic viscosity also is neglected. So, we have just substituted for mu just epsilon, rho into epsilon, and when I divide this equation by rho, I do not have any rho here. So, this is what we are going to substitute for the mu now. Rho, there is mu equal to rho into epsilon. Okay. So, this will be equivalent to nu turbulent. Okay. So, that is the turbulent kinematic viscosity for turbulent. So, now this again you can see the continuity equation. So, you see the similarity between the laminar counterpart. So, we can replace the molecular viscosity in the laminar solutions by this eddy viscosity and we can go for prescribing the solution. Do you understand? So, when I write the equation for the turbulent jet, I have to replace by the above concept, I have to replace the mu by mu effective, correct. So, mu effective is nothing but the dynamic viscosity molecular level plus the eddy viscosity. Now, since the dynamic viscosity is much smaller than the eddy viscosity, we neglect this and write only the mu effective as rho into epsilon, and by dividing this equation by rho, I get the epsilon here. So, Vx into dou Vx by dou x, please understand these are all mean quantities, plus Vr into dou Vx by dou r will be equal to 1 by r dou by dou r of r epsilon dou Vx by dou r. So, this is the equation I get. So, you can see this is similar to the laminar jet axial momentum conservation, and the continuity equation also is the same when you just see the mean quantities are put in here. So, they are the same. So, the solution of laminar jets apply here, but only thing is we have to replace the mu by rho into epsilon. So, the solution again we go for the same similarity variable, which is dependent on we have defined this is dependent on r by x, and and the initial jet momentum is same. Okay, rho e v e, that is exit velocity, the density at the exit of the nozzle into the area of cross section of the nozzle or the port, which is pi r square. So, this is the initial jet momentum. Okay. So, similarity variable is already written, but please see that the mu term which was used there. So, this is the mu term which was used in the laminar, that is now substituted by the eddy viscosity. Okay. So, everywhere else I do the same. So, similarly we got the solution for the axial velocity Px. So, that is now replaced, now the same equation is written, but the mu part is now replaced by this. Similarly, wherever I have indicated this, you can see that so here also the Reynolds number was used basically. So, VE or by mu, you can see that this is now replaced here. So, actually this should be rho VE R divided by this, so rho cancels. So, we get VE R by epsilon. So, you can see this. So, the Reynolds number is now written like this. Similarly, here also the Reynolds number was there. So, 2.97 into Reynolds number of jet power -1. So, now Reynolds number is replaced by this because rho cancels. So, we can see that the solution what we got for the and please understand these are the variations of the mean quantities only. Basically, we are interested only in the mean quantities. So, the mean quantity variation. So, all are mean quantities. Please understand everything is mean quantity here. Okay. So, the mean quantity variation is what we are interested in. So, that is got by just applying the laminar solution. However, replacing the dynamic viscosity, molecular level dynamic viscosity by the eddy viscosity rho into epsilon. So, that is the way followed. So, it is simple in this. So, in this context it is very simple. However, the only problem is how to evaluate this value epsilon. Okay. So, the eddy viscosity can be determined by Prandtl mixing length. As I told you, Prandtl mixing length concept. So, actually Prandtl what he told was if you take velocity variation like this. So, Prandtl postulated a length called mixing length. So, this is say LM mixing length, and so for example, in this the velocity may be u dash, and here it is u dash, say this I will say at a particular y, and u dash at y plus LM. So, some packet of fluid when it this is the these are all going to flow in this direction. So, I need not put u dash, I say u. Okay. So, these are the layers which are going to flow parallel to the mean quantities, but the fluctuation quantities are going to be there. So, for example, if there is a v dash fluctuation, then that will contribute to some packets coming across the transverse direction. Okay. So, that Prandtl assumed that due to these y directional fluctuations, the packet can travel at most a length what is called the mixing length. So, with that assumption, basically the epsilon can be evaluated. So, for this particular context, the jet spread, we can say that the R half, that is the jet half width, grows proportional to x. We have seen this, correct. So, this is the jet exit, and this is jet axis, and the jet spreads like this. So, if you take R of, so we can say R of also comes something like this here. So, R of increases with the grows with the x, grows proportional to the x direction. So, this is the x direction. So, and R of grows increases as x is increased. However, the central line velocity, axial velocity, okay, this is Vx 0 means Vx at r equal to 0. So, central line velocity at the axis decays. So, you have seen after the potential core. Anyway, this solution is not applicable near to the jet exit. So, far field only it is applicable. We have seen that Reynolds number also 0.375 into Rej. If that is the location, then from that location onwards, this solution will be valid. So, in that region, you can see that the decay of axial velocity happens, mass fraction, axial velocity, etc. happens in that. Okay. So, based upon this, the epsilon can be returned in terms of constant times R of the particular x and V x naught, that is the actual the central line velocity at the particular x. So, this we can write. Now, using this solution, we can write equations for R of and V x naught and try to get the values in terms of VE and the radius. So, that is what we are going to do this. So, please understand that the as per the Prandtl mixing length concept, a mixing length is defined where the velocity gradients are used to get the epsilon values. So, using that concept, we can derive this basically to get epsilon value for this jet spread as a constant time r of at a particular x and v the central line velocity at the x. Okay. So, now let us try to write this. Okay, the velocity dk, you can see that Vx by Ve normalized by the jet exit velocity Vx naught by Ve is equal to 13.15 times x by r power minus 1. Similarly, jet spread rate is a constant. Okay, when you just put here, okay, the values, you can see that is a constant here. R naught by x, when you substitute this epsilon value in these equations. So, this equation and this equation, you substitute the epsilon values, okay, then you get these two. So, from that you can see that the epsilon value will be, that is what when we postulated this problem, we told that we will use a constant eddy viscosity for this solution of the turbulent jet. So, anyway, a lot of simplifications have to be put in when you derive a theoretical solution for a complex problem. So, that is what we are trying to do here. So, when you substitute this in the Vx by V equation and set r equal to 0, similarly r of by x and substitute this, you get these equations, and finally you get the epsilon value as a constant 0.0285 times V into r. Okay. So, we can understand that for a turbulent jet, neither the velocity decay nor the spreading rate, okay, this ratio is spreading rate, depend upon the jet Reynolds number. Okay. That is, this is actually not for just transition regime or anything. It is actually in the strong turbulent regime. So, for example, the Reynolds number should be very high. When this is very high, we can get the solutions. Okay. So, these are all far field solutions applied to very high Reynolds number. So, that we have to keep in mind. Okay. So, we can see that the so in the laminar jet case, the velocity decay was directly proportional to the jet RE, but here you can see that the velocity decay is not. So, that means that the turbulent jet is independent of the nozzle exit conditions. So, exit means nozzle exit conditions. So, that is very important to understand here. So, the eddies which are going to be present after the potential cohesion, basically that is going to contribute to the characteristics of the turbulent jet. So, we can see that the spreading rate is a constant. Once you get past a particular Reynolds number, for all the Reynolds numbers, this characteristic will be intact. So, that is the main thing we have to understand from the solution.